Hello. So for this video, I'm basically just going to go over the first section of the Exam 2 study guide, and the images over here. So I'll just start from the top, work my way down, try to go into all the details, give you guys everything you need to know to be successful. And so today I'm going to make it over part 1, energetics. Maybe in a couple days I'll do one over whatever the next one was. I think metabolism, and then I'll do one over photosynthesis, which is the third one. So this shouldn't take too long to get everything out, so we'll just start right away. So energy is the capacity to do work, and there's two types. There's kinetic energy, which I'll just be writing as KE, and there's potential energy. So this is a good way to think of it. Just think of potential energy as something that's high. So we'll say this is potential energy, and as it falls, that's kinetic energy. And in biology, this is going to find importance in bonds. So I'm going to make a little table. So when it comes to bond, less polar equals longer bond equals so the more polar something is, the shorter its bond is, and the less potential energy it has. And the reason that is because polar bonds are very low energy, and that's why they're so favorable and they happen all the time. So when that bond is formed, it's a very low energy bond because it's so stable. Whereas a less polar one is going to be a lot less stable, and it requires more energy to hold those atoms together. So when you break the bond, a lot more energy is released. So a great thing to look at when you're thinking of these things is ATP, which basically looks like this, and you have your sugar and your base, and then you got your double bonded oxygens, whatever. You guys know the rest. So these bonds right here will have a lot of potential energy, and that's why ATP is so good for energy. So we'll go on to the next thing. We'll do two examples. So we'll say we have CO, then we have so we have a ketone, a methane, and a propane. So this is polar, this is nonpolar, and this is nonpolar. So we know right away that this one is going to have more energy in its bonds. And then this one over here is basically the same as methane, but it's three of them. It's propane. So it has a whole lot more bonds, so it has a lot more energy held in those bonds, which means this one has the most energy. And if you guys are kind of confused about thinking about this, how to conceptualize this, think of something like water, and what happens if you put a lighter to water. nothing's going to happen. Most likely the flame will go out. And think of if you put a lighter to propane, it's going to combust, it's going to explode. So that just shows you how unstable these bonds are and how much energy they have. Water is a more stable bond, so it requires a lot more energy to break it up. Whereas propane, methane, they're just going to fly apart basically. Okay, so next we'll go over the thermodynamics. So we have the first and the second. So I kind of dumb these down a little bit. I like to think of it simple like this. I honestly don't even have the first and second memorized. I just have the concepts of them memorized. So the first law of thermodynamics is basically stating that the energy in equals the energy out. If I push a sled with 10 pounds of force, then the sled is going to push back with the same amount, and it's going to go forward whatever the excess movement is. If an electron goes from an N4 orbital to an N2 orbital, it's going to decrease its energy, but in doing so there's energy given off. So then the second law is that spontaneous reactions lead to an increase in entropy. So basically everything in the universe, because the universe is like a closed system, is how it's viewed in physics and thermodynamics and stuff. So everything that happens spontaneously is going to increase disorder. So entropy is so yeah, this explains the hydrophobic effect. And when I like to think of entropy, I always think of just like a house or your car. If you don't clean it, you don't put energy into the system, you just let spontaneity happen, it's going to get dirtier. I've never seen a room that gets cleaner without cleaning it up. That'd be cool though to have that. So we're going to go into macromolecules and subunits. Oh no, we're going to do a free energy diagram real quick, just so you guys can check that out. Okay, so this is a free energy diagram. So we have delta energy, which is just a change of energy, and I'll draw a couple reactions. So the first one, okay, so we have three reactions. We'll say 1, 2, 3. So 1, this is your reactants, and this is your products. Reactants, products. So 1 is endothermic. It goes from low energy to high energy, which means energy went into the system. So 2 is exothermic. It went from high energy to low energy, which means energy left the system. Now 3 is just as exothermic as number 2. The same amount of energy is released, but it's just catalyzed by an enzyme. So the enzyme lowered this, basically stabilized the transition state, and in doing so, it lowers the energy required to get to the energy state or the transition state and get past it. So these would be spontaneous, and this would be non-spontaneous. Okay, so now we're going to go over anabolic and catabolic reactions. So I'm just going to draw okay, so these are your macros, and these are your, we'll just say subunits. Okay, so when you go from many little things and you make a big thing, that's anabolism. Think of anabolic steroids. You have a little guy, and then all of a sudden he's huge because he was on anabolic steroids. And when you're on anabolic steroids, you have to eat lots of food. And you have to eat lots of food because you need ATP to make this happen. Okay? Now, when you eat all that food, you're eating macromolecules, and you're eating macromolecules, and that's going to get broken down to produce ATP via catabolism. So it's kind of a cycle. Anabolism requires ATP. So anabolism, think of it as growing, requires energy. It requires ATP. But in order to get that ATP, you have to consume food, which gets broken down to create ATP. So it's a pretty fine balance, and it's pretty cool how all that works. Okay, so one more thing with this. Here we go. So up here, we're going to have a alright, so we have cool. Drop my pen. Okay, so when we go from a subunit to a macromolecule, there's going to be a decrease in entropy, but an increase in enthalpy. And when the vice versa happens, and you get it broken down into subunit, there's going to be an increase in entropy. There's going to be more disorder. So I'll give you a second to write this down. Next, we're going to make a graph using Gibbs free energy and all that. Alright, so if you don't have it written down, pause the screen or whatever. I'm going to erase all this. Okay, so Gibbs free energy is change G equals, boom, just like that. So this is a table that I used in biochem, and I think it helped a lot. I like to do change of H, change of S, plus plus, minus minus, plus minus, plus minus. So both of these are plus plus, which means think of a number line. Plus plus is going to be a big number. So this is spontaneous at high temp. Minus minus, it's a very low number. Spontaneous at low temp. Now if entropy is decreasing and enthalpy is increasing, this is going to be non-spontaneous. And vice versa, if entropy is and this is at most temps. There's extremes, okay? There's extremes with any situation. So that's why I say most temps, because you could increase the temperature to infinity and eventually it's gonna happen. So then over here, spontaneous at most temps. Because once again, this could be spontaneous at I don't know, 0 kelvins, but if you go to like an absolute 0 or something crazy, it's not going to be spontaneous. And then with G, alright, so negative gives free energy, it's spontaneous. Positive is non-spontaneous. So this is also energy released, and then with this one, energy consumed. Alright, so next we'll talk about enzymes, what they are, what they do, what the active site is, predict how changes in active site chemistry, all that stuff. So, what is an enzyme? An enzyme is something, we'll draw it as this blob. And we'll say these are the active sites right here. Boom, these are active sites. So what a enzyme does is it takes a reaction that, we'll say a reaction that has a change of G of 2. And then the enzyme will have a change of G negative 4. Boom, now it's spontaneous. And this is called reaction coupling. So an enzyme couples reactions to make something that is non-spontaneous happen spontaneously. So the active site is where the substrate binds. So here, this is our substrate. It'll come in and bind in here, and then you'll have something like this. And then so once this happens, then maybe your enzyme will turn to that. So basically, this to this, but then this way, so just know that an enzyme is going to lower that activation energy. So let's see how this would look on a energy diagram. Okay, so we have our reactants here. Let's draw them a little higher up. So we have our reactants here, and they're going to go over this little bump, and they're going to come down. So this is changing energy. Okay, so what an enzyme will do is it will lower this right here. So that's the energy for activation. And maybe there just wasn't enough energy. There wasn't enough energy to make this happen. So we'll say it was a non-spawn. But there was enough energy to make this happen. And that's due to the enzyme holding that reaction and making it actually happen. And remember, this doesn't tell you, this right here doesn't tell you if it's spontaneous or not. This just tells you that if it's exothermic, or sorry, exogonic or exergonic. So in this one, you can see energy is going to be released from the system. So if you have an active site, and actually I'll draw it all out just so you can write it down. Okay, so if you have a hydrophobic active site, and then it goes to hydrophilic, that is not going to work. Your active site chemistry needs to remain the same. If you have a hydrophobic active site, that's because the substrate is hydrophobic. So if all of a sudden you switch that active site to hydrophilic, you're going to shut that thing down and it's not going to catalyze that reaction. If your active site is charged negative, that probably means your substrate is charged positive. So if you switch it from a negative to a positive, now instead of attracting that, it's going to repel your substrate. This can be good and bad. If you want to shut off somebody's enzymatic pathways or something, maybe you can find a way to engineer a different active site that doesn't do that. That'd probably be used more in research and not in actual medical applications on humans, because that'd be pretty messed up to turn somebody's, just play around with somebody's enzymes like that. Yeah, so modifying the enzymatic activity is useful in research, and this is basically how you would go about doing it. We know that an enzyme is a protein, and we know that proteins are created from the translation of RNA, which is created from the transcription of DNA, and we can edit DNA. So because we can edit DNA, that basically means we can do whatever we want with whatever living system we want in the entire world. So it's like a big game of Legos or something. So that's enough for that tangent. And I think that's good for this. I think we covered all these points. If you have any questions, just shoot me an email. And that's it for this video. So take it easy. Have a good weekend. And I'll see you Tuesday.